Investigate acceleration. To determine the acceleration of a trolley using a trolley, ramp, hanging masses, string connected to it, a card on top of the trolley which goes through the light gates, crumpled paper on the ground so that obviously it doesn't cause any damage, it's really just a precaution, and then the light gates connected to a data logger. That will essentially help us determine the acceleration, calculate it for us using a change in velocity in a certain time. Okay? First thing we need to do, if I'm investigating the acceleration of this trolley, then I'm going to use the equation F equals ma. If I rearrange that for A equals the force, which is the resultant force on the trolley, remember, Newton's second law, okay? Resultant force in the direction of the acceleration, so that way, divided by the mass. Now, if I want to investigate how the mass affects the acceleration of the trolley, I have to keep force constant. I can't have both variables changing at the same time. It's not a fair test. I don't know which one is actually causing the acceleration to change, so I have to keep one fixed. If I want to know how mass affects A, then I keep the force the same. Where's that force coming from? So, if I have the trolley on a flat bench, then the forces currently acting on the trolley are weight vertically down. There'll be a normal contact force acting up, which if it's horizontal will perfectly balance the weight. Because these hanging masses have a weight down here, there is a tension in this string which is pulling the trolley and making the trolley literally accelerate along the ground. Okay? So because there is a tension in this string pulling the trolley to the right due to the weights of the hanging masses, that's why the trolley accelerates. So if they ask you why does the trolley accelerate? Because there is a resultant force. Remember, nothing accelerates if there's no resultant and the forces are balanced, then either it's moving at constant speed or it's stationary. So if the trolley is accelerating, one, there must be a resultant force. Two, that's provided by the tension in the string. Okay? But we know the tension in the string is exactly the same as the weight of these hanging masses. So tension equals the weight of those hanging masses because that's what's providing the tension. Okay? So I know the force pulling the trolley along to the right, the weight down, the normal contact up. They do not have anything to do with the trolley's motion to the right. They're perpendicular. This force here, the weight of the trolley, does not contribute to the tension. Okay? It doesn't add anything to the tension. Alright? There may be a frictional force acting backwards, but we're going to find out if that's actually present when we investigate this thing. So acceleration with mass, keep force constant. Which force do I keep constant? I need to keep the tension constant. Okay? In order to keep the tension constant, all I do is keep the hanging masses constant. So what I want to do at the start is put enough hanging mass on here, calculate its weight by timesing it by 10g, and then that's my tension in the string. Keep that fixed while I'm investigating mass. Okay? The mass that I'm investigating is going to be on the trolley. Okay? If I add some mass to the trolley, I let it go again, same hanging masses, same weight in the string, so same tension, and then obviously it will cause the trolley to accelerate. Then I add some more mass to the trolley, and I calculate the acceleration again, and I keep adding mass whilst keeping this hanging weight, therefore the force, constant, and I see what that looks like on a graph. How does the mass of the trolley affect its acceleration with the same force? Okay? How do we expect it to affect it? You'd probably guessed if I increase the mass, surely that's going to weigh it down and that will probably slow it down and it will reduce its acceleration. So let's have a look. The graph that you get looks something like that. Okay? Now you know that's an inverse proportion. You know you can say very confidently, if you want to make a conclusion about how mass affects acceleration, looking at this graph, if mass increases, which is the mass on the trolley, increases, then the acceleration of the trolley decreases. Okay? But just looking at it from a mathematical point of view, you might say it looks like mass is inversely proportional to acceleration. Now it looks like it, and it may well be, but you don't know that unless you plot a graph to prove it. Now a question in the exam could say, make a conclusion about the mass and the acceleration of the trolley. Mass goes up, acceleration goes down, no problem. Okay? But if you want to make a better conclusion, you need to look at the shape first of all and decide, does it look like it's an inverse relationship? Does it look like it's a squared relationship, like a quadratic graph that you see in math? Does it look like a cubic relationship? Or does it look like the root of x, for example? Alright? First of all, look at what the shape is. If I look at this, instinctively I say it looks inverse. Now how can I prove that? By plotting a graph. If I want to prove that A is inversely proportional to M, then I have to plot A against the inverse of M, 1 over M. Now if I say A is directly proportional to 1 over M, which is the same as saying acceleration is inversely proportional to mass, then the graph that I should get, if this is true, is a straight line through the origin 0, 0. Remember, the definition of direct proportion is straight line passing through the origin 0, 0. Okay? If my prediction is correct, my conclusion, if I want to say that it's correct, I have to plot A against 1 over M, which is the inverse of M. If it's a straight line through the origin, then yes, acceleration is inversely proportional to mass, or acceleration is directly proportional to 1 over mass. That's the same thing. Okay? So that's not a problem. We've proved that. There's the first graph. We've said yes, increasing mass decreases acceleration exactly as an inverse function. Okay? The second thing that I wanted to investigate was how does the force affect the acceleration on the trolley, in which case I have to keep the mass constant. So investigating acceleration with force, changing force, increasing the force, or resultant force, I have to keep mass constant. Okay? But what mass? 9 times out of 10, people will say, just put some mass on the trolley and keep it the same. And then just keep adding weights or masses to the hanging mass and increasing the force, the tension in the string. Okay? Yes, that will increase your force, and yes, that does keep the mass of the trolley constant, but this just isn't just mass of trolley must be constant. It has to be anything that accelerates, the mass has to be constant. And what's accelerating? The trolley accelerates along the ramp, but the masses accelerate down. Yeah? The only reason the trolley is accelerating is because those hanging masses are accelerating down. So if I want to keep the mass of any accelerating object constant, I have to keep the combined mass of trolley and hanging mass the same. But at the same time, I have to increase the force on here to increase my tension. So how do I keep the total mass of trolley and hanger the same whilst adding mass to the hanger? Okay? And the way that we do that, we add all the mass to the trolley at the start. So any mass that is going to go on this hanger in order to increase the force. So I'm literally going to place masses on this hanger to increase the tension in the string, but I have to make sure that the mass at the start of both is the same throughout the whole thing. Then I put all my masses on my trolley at the start. Let's say I'm going to put 10-gram plates on my hanging mass. I'll put all 10 on top of my trolley at the stop, okay, or into my trolley. And then what I'll do is I'll send it down the ramp if it will pull it. Then I'll take a mass out of my trolley, take it to the hanger and put it on. That increases my force by 10 grams, which is 100 newtons, okay? Or, that's a lie, in kilograms it would be a bit less. 0.01 times 10 instead, so 0.1 newtons. But the mass before here was 100 grams and 0 grams, right? Combined mass, all my weights were in here, 100 grams plus 0 grams, and then I took 10 grams from there, I put it on there. My force went up, but my combined mass is now 90 plus 10 is still 100. So I am conserving mass of trolley and hangers because they're both accelerating, okay? But I'm increasing the force that is pulling the trolley along the ramp. So, how do you expect increasing the force in the string will it affect the acceleration of the trolley? You'd expect it to increase, okay? And according to that equation, F equals ma, if I've kept the mass, combined mass, constant, then F should be directly proportional to acceleration. So the graph I should expect would look like that. The one, however, that you get looks something like that. Yes, for small forces, the acceleration does increase and it appears to be a straight straight line, and yes, it goes through the origin. So here, you could say that F is directly proportional to A as expected, but for some reason as force passes a specific point, it gets too big, then something happens. The acceleration increases, but it plateaus, it stops increasing at the same rate. It actually increases less and less every time. And there has to be a reason for that. And we go back to our diagram where we said the only forces acting on the trolley are weight down, normal contact up, not affecting the acceleration, so not affecting my investigation, and then resultant force, F equals ma, which is T, the tension in the string. However, if something is affecting the acceleration as force gets bigger, meaning that it's not directly proportional, there has to be some sort of frictional force. Now, questions to think about. What about this graph? What feature of this graph suggests that there is friction acting on the trolley? And it's the fact that it is curved. If this line was a straight line as expected through 0, 0, then I would assume there is no friction or the friction is negligible. But if I'm asked in an exam, looking at that graph, how can you tell there must be friction acting on this car, this trolley, and it is actually having an effect at large forces? Then it's because the graph is curved. And because the graph is curved, there has to be a frictional force that is making some difference to my results. So, the next question is, I don't want this friction to affect my results. I don't want the friction to have a part to play in my graph because it's making it curved. How do I remove the effects of friction? And it is not using lubrication, it's not changing the surface to a smoother surface. What I have to do is I have to be clever, I have to incline or raise my ramp. So in order to reduce or remove the friction acting on the trolley, I raise the ramp. Now why did I do that? If I raise the ramp, the weight still acts vertically down. But because my ramp is on an incline, my normal contact force is acting perpendicular to the surface. If I get rid of the string, I don't add the string yet, there's no tension in the string pulling the trolley down the ramp. There's a frictional force up the ramp. But because this weight is acting vertically down and my ramp is inclined, there is now two components of my weight. Okay? Because this weight now acts at an angle, and if the force acts at an angle, there are two components. Okay? If I have no string on here, this trolley will still roll down the ramp. That means there must be a force pulling it down. The only force acting on it that could pull it down is the weight. Didn't happen here because it was perpendicular to tension and the trolley was moving to the right. Okay, so that weight had no effect on the trolley's acceleration. However, if I raise the ramp, the weight is now acting at an angle to the slope, which means part of the weight is going into the slope, which balances the normal contact perpendicular to the slope. And then a fraction or a component of my weight is actually pulling the trolley down the ramp. Now, what I want to do is raise the ramp to the perfect point where the component of weight balances the friction up the ramp. Because if the weight down the ramp, the component of the weight acting down the ramp equals the friction acting up the ramp, the forces will balance. There's zero resultant, which means the trolley will go down the ramp at constant speed. Okay? Therefore, if I have balanced forces here, I have cancelled the friction out with the component of weight down the ramp. Zero resultant force now. If I add the string back, put my pulley system back in, put the string in, add the hanging masses back again, I have a tension pulling the trolley down. Every time I move a mass from the trolley, add it to the hangers to increase the tension. The only force contributing to the acceleration of the trolley down the ramp is the tension. In this situation, as you can see, the friction was having a part to play. My resultant force was tension subtract friction, but that wasn't a constant increase. Okay? The factor of friction actually affected my results, so it wasn't straight. If I raise the ramp, the component of the weight balances the friction so that there's zero resultant and the trolley would move down the ramp at constant speed. Now if I put the trolley back, add the string, keep increasing the hanging masses, so I increase the tension. The only resultant force contributing to acceleration is tension. So the graph that I will get now is exactly what I expected. Through the origin, straight line. Okay? F is directly proportional to acceleration. Okay? And that's it. They could ask you questions that involve not actually investigating the acceleration using light gates and using a raised ramp, for example. But what they could do is say, how could you determine the average speed? In which case, all you need is the distance of the ramp using a meter rule, a stopwatch to measure the time that it takes to travel from one point to another, okay? And then you use the equation speed equals distance over time, and that's the average speed, okay? One more thing, how do I know that I've raised the ramp high enough so that the component of weight perfectly balances the friction? How do I know when it rolls down the ramp at constant speed? All I need to do is raise the ramp slowly to the point where the trolley just starts to move, okay? It's the best way that I can do it without using computers and calculations. Just slowly raise the ramp, and at the point where the car literally just starts to roll down, you can assume that that is the perfect point where it rolls down at constant speed, so the component of weight equals friction. Friction is no longer a part of the equation, okay? Add my string back, move the mass from the trolley, add it to the hanger, and I increase force, which is directly proportional to acceleration now. There is no effective friction on this anymore, okay?